Hey guys, welcome back to a quick code. Today we're doing another Brainstellar Quant puzzle. This one is called Prisoner's Hat, the multicolor version, or rather the second version of this particular type of problem. We've already done the first type. It's within the easy problems. So this is a medium problem. This is the second type of this particular kind of problems. You guys can pause and go over the problem once. So to explain the problem first, we've got 100 prisoners lined up in a straight line, and each of those 100 prisoners are assigned a random hat from a set of 10 unique hat colors. Now, it's not explicitly mentioned in the problem, but the prisoners beforehand already know the 10 colors of the hats. So they already know that one of either red or blue or green, and just assume any 10 colors like these. And the prisoners are allowed to create a strategy before the game starts, and the prisoners already know the set of the 10 different colored hats, from which each prisoner will be assigned a particular hat color. Okay, so we've got 100 prisoners standing in a line like this, and the game is starting from the 100th guy. He has to guess the color of the hat that he is wearing. He obviously can't just look up and see his own hat color, but he has to guess that. And if he guesses it correctly, then he gets to survive, or else he will die on the spot. And then prisoner 99 does the same thing, 98, and all the way down to prisoner 1. Now, the trick is that the prisoner 100 can't see his own hat color, but he can see the hat colors from P99 all the way to P1. P98 can see the hat colors from P97 all the way to P1. And similarly, going down the line, P3 can see the hat colors of P2 and P1, while P2 can see the hat colors of just P1, right? So you basically can just see the hat colors of the people standing in front of you. And it's also important to understand that they can hear each other's answers. So P1 could be hearing to P100's answer, P99's answer, P98's answer, all the way up to P2's answer before he makes the decision, which will be the final decision about his own hat color. So everybody can hear everyone else's answers. But the answers are set in this particular order where it starts from P100 and then P99 and then P98 and it goes on forward. Now, the question that we've been asked is to first of all come up with a strategy which could be used by the prisoners to help release the maximum number of prisoners. We have to come up with a particular strategy. So, coming towards the hints now, first of all, the maximum number of prisoners that we were guaranteed to be able to release is 99. This is the answer which is pretty similar to the answer for the first problem. And the second hint, in my opinion, is that the solution to this problem is very similar to the strategy we used in the previous problem. So right now, I ask you guys to pause and go watch the previous video. I'll be putting a link to that problem in the description down below. So a few more hints. First of all, let's forget about colors and assign each color a distinct number. Now, what do I mean by this? Well, according to the prop, there's a particular set of 10 unique hat colors, right? So there could be red, blue, green, yellow, violet, and so on. Now, what I'm trying to do is to forget these colors because talking in terms of colors won't be very useful for us. So let's just assign red as 0, blue as 1, green as 2, yellow as 3, violet as 4, and so on. So we would have different types of hats with numbers assigned from 0, 1, all the way down to 9, right? Because this becomes a set of 10 unique numbers. So what the game eventually becomes now is that each prisoner is assigned a random digit hat, a hat with a random digit from 0 to 9 on it, and the game becomes that that prisoner has to guess the digit on his own hat. Now you can easily map this to colors, right? So for now we're just thinking in terms of digits, but this could be the exact same talking in terms of colors. It's just that it's easier to talk in terms of digits. So from now on, we're going to assume that each one of them was assigned a random digit from 0 to 9, and the game is to guess that particular digit. So now to introduce more notation to make the problem simpler, from now onwards, each prisoner, so for example PI, by the digit that he might have gotten. So PI would be noted by either 1 or 0 or 2 or something like this. So basically I'll be saying so like PI is equal to 5, right? Or something like that. So this just means that PI was wearing a hat of color associated by 5. Or for our purpose, we could just say that PI was wearing a hat which had the digit 5 on it. Now, another hint is that, so in the previous problem, we used a binary pattern where we basically used a function or a pattern which had a base of 2, or rather, I would say that it had two unique values, and the function or the pattern oscillated or alternated between those two values, right? Now, over here, since we have 10 different digits and 10 different values that we need to represent, we need to find a function or a pattern of base 10. What I mean by base 10 is that the function must have 10 unique values and would loop around those 10 values. Very similar to the way our function chosen for the previous problem was working. And if you think hard about these two properties of having 10 unique values and looping around those 10 values, we come to a particular probable function that might work of using a sum modulo 10. By the way, modulo means that taking the remainder with 10. So if let's say my sum is equal to 48, then 48 modulo 10, in computer science, this modulo is used a lot basically, would be 8. So basically what I'm just doing is I'm going to use a function where it sums up some values and then it takes the remainder. This could also remainder with 10. This could also just mean that you calculate the sum, right, and you take the very last digit. Now, as you can see, this could be anywhere from 0 all the way up to 9. So this becomes 10 unique values. And from 9, the next value becomes 0 again. So there's a looping property between these values. So remember that the function we're going to use is sum modulo 10, where modulo basically means taking the remainder. Now, I'm going to denote the sum of all the values a prisoner sees in front of him, modulo 10. We're going to denote this by, let's say, S of I. What S of I denotes is the sum of all the digits that the ith prisoner can see in front of him, and then eventually you do a modulo 10 so that this property that we talked about over here can be applied. So mathematically this would look like something like this, right? And as you can see, Si in itself will also be a value from 0 all the way to 9, and this will also have that looping property. Now if you think about it closely, can I say that Pi already knows the value of S of I? Try to pause and think about this statement. Well, yes, because Pi can already see all the guys from P1 all the way up to P of I minus 1. He can add up the digits he sees on their hats and do a modulo 10. So Pi already knows the value of Si. Now, if I somehow provide Pi with the value of S of I plus 1, could this information be used to help Pi calculate his own value? Can these two values deduce the value of Pi? Try to pause and think about it. Well, let's take a few examples to illustrate this point. Let's say S of I plus 1 was some integer which ends in a 6, and S of I was some integer that ended in a 3. Now, seeing these two values or knowing these two values, we could deduce that Pi is equal to 3, right? It can't be any other value. For example, let's say S of I plus 1 is 66 and S of I was 63. Now, you can see that obviously in this case, Pi is equal to 3. And by the way, S of I can't be any other value. It couldn't be 73 because that's impossible. Or it couldn't even be 53 because that's also impossible. So it doesn't really matter on the other digits, right, over here and over here. All it matters about is these two digits, the very last digits. And using the very last digits of two sums, we can always, two consecutive sums by the way, we can always deduce the Pi value. To take another example, so let's say both of them were ending in a 6, or S of I plus 1 actually has a value of 6 and Si has a value of 6, right? Actually, these values won't even be conveyed within S of I plus 1 and S of I. S of I plus 1 is going to be 6 only and S of I is going to be 6 only. So using these two values, we can deduce that Pi was equal to 0. Or let's say S of I plus 1 was equal to 6 and S of I was 9. In this case, we can still deduce the value of Pi. Well, it can't be minus 3, right? Because our mapping is from 0 all the way to 9 for Pi values. So it could only mean that the actual sum was, let's say, 66 and the new sum is 59, which means that the pi value is 7, right? So no matter what the value of s of I plus 1 and s of I is, we can always deduce the value of pi. Thus, we conclude that since pi already knows the value of si, all we need to ensure that pi knows the value of s of I plus 1. And this is where our induction is about to start. Just focus on the point that p of I just needs the value of s of I plus 1. If he knows the value of s of I plus 1, he can perfectly deduce his own pi value. Now what happens is, since we need a base case, P100 sacrifices himself by creating the base case by announcing the value of S of 100. How does he do that? He basically counts up the values from P1 all the way up to P99, adds them up and does a modulo 10, and let's say the value comes out as 8. So he just shouts out 8, right? Now, there's a 1 by 10 chance of this actually being the hat P100, but this doesn't matter. He's sacrificing himself. So there's a 9 out of 10 chance that he dies, but that's not important over here, right? He shouts out 8. So what this does is now P99 knows the value of S100, which is 8. And P99 also knows the value of S99, since he can just calculate that. And let's say that comes out to be 7. These two values would deduce that P99 is equal to 1. And so P99 is going to shout out the value 1 and it's going to be correct and he's going to be saved, right? Now what happens? From the perspective of P98, he knows that S100 is 8 since that's the value 100 shouted out. And he knows that P99 value is 1. Now using these two values, he can calculate the value of S99, which would actually be 7, right? So that means that now he knows S99. He already knows S98. Now using these two values, he could calculate P98. And now the induction just keeps on working. Now P97 would use this information of S100, the information of P99, and the information of P98 and deduce the value of S98. And he already knows S97, and so he shouts out the value of P97. And this process keeps on continuing. And using this process, all the values from P99, P98, all the way down to P1 are guessed correctly, and all those 99 prisoners are freed as a guarantee using this strategy. I hope you guys understood this solution, and thanks for watching.